Ladies and gentlemen, welcome back to the ISITIA 2021. I hope you will went up again to continue to one of the main agenda of ISITIA 2021. I would like to invite Professor Muhammad Azari, Director of Institute Technology 10 November ITS. Ladies and gentlemen, please welcome Professor Muhammad Azari.
Thank you very much. Ya, terima kasih. Good afternoon and good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat siang dan salam sejahtera untuk kita semua. The Honorable ITS senior leaders, especially I see here Pak Dr. Keynote Edi Purnama, the Dean of Faculty of Intelligent Electrical and Informatics. Also our guest, a special guest, Dr. Adi Dharma, Dr. Dhani Pujianto from UK, London, Professor Wolfgang Boss, Professor Xiang Hu Yu from National Sun Yat-sen University, Taiwan, all the Honorable Conference Chair, Pak Febi, and also distinguished guests, keynote speakers, colleagues, all participants. It is a pleasure to welcome you to our event here, virtual, of the 2021 International Seminar on Intelligent Technology and its Application, or ISITIA 2021. Ladies and gentlemen, this event is very interesting because today we have two speakers in 2 days. The reason is because these 2 days we have a keynote speaker that from different location, that time is much different. So we separate into 2 days. So at this time, I would like to express our gratitude to all speakers, especially Dr. Adi Dharma, my colleague, Dr. Dhani Pujianto from UK. Thank you very much. Professor Wolfgang Boss, thank you very much. And also Professor Xiang Hu Yu from Sun Yat-sen University, Taiwan. ISITIA is an international conference hosted by the Department of Electrical Engineering, Faculty of Intelligent Information and Electrical Engineering, ITS, Institute Technology 10 November. Because of this COVID, especially now, we are in the second phase of pandemic, that the new cases confirmed positive now is being reduced compared to 3 or 4 days ago. 3 or 4 days ago, the new cases was more than 50,000 per day. But I watched from the television last night that the new cases now reduced to 38,000 new cases per day. So this is good. Ladies and gentlemen, that's why this is the reason that Pak Febi, the General Chair of ISITIA, hold this conference in virtual. By hold this conference in virtual, we may miss the opportunity to visit ITS and also Surabaya, but I hope the networking and collaboration still can be initiated and better. So now, because of this technology, we can meet together in this online media. So ladies and gentlemen, ITS, Institut Teknologi 10 November, is a public university established in 1960, and currently we have 21,000 students, including international students from more than 30 countries. The vision of ITS is to become a world-class entrepreneurial university. So the achievement, according to Times Higher Education Impact Ranking in 2020 to 2021, the ITS position in Impact Ranking Times Higher Education is the first in Indonesia, means is the best university in Indonesia, and we are in the position of 64th in the world. This impact ranking concern about the university program relates to SDG, Sustainable Development Goals. During the pandemic that in Indonesia, it was commenced in March, middle of March 2020, and then become very low, almost zero in around April, but now increase again. It's very dramatically. ITS, with collaboration with Airlangga University, especially in the hospital, education hospital run by the Airlangga University, we built a robot assistant for hospital. We call it RISA. This robot to help the doctor and nurses to bring some clothes, medicine, or equipment to the room, the isolation room of the patient. So this robot can minimize the transmission COVID from the patient to the doctor. So we have already used or produced this robot for hospital. It has been used in more than 17 hospitals from Bali, Java, until Lampung, Sumatra. Or at the moment, there are 7 provinces using this kind of robot. So our team now to address the shortage of oxygen, because within these 2 weeks or 4 weeks in Indonesia, we have a shortage of oxygen because too many people, too many patients need the oxygen, but the reserve was shortage. Our team from ITS now is working together with Australia and India. Australia is especially with Curtin University, Monash University, also with India University, to address this kind of shortage. We built a low-cost oxygen concentrator. Hopefully, we can finish it immediately. Now we are looking for the zeolite for the filter. Everybody, if we can help together, working together to address this oxygen shortage for our society. So this is the current condition in Indonesia, and also for us, university, that we have to help our community to address kind of a shortage oxygen, etc. And then this innovation of COVID-19, it has been launched by ICT Robotic Technopark. So in ITS, we have 4 clusters of Technopark. The first one is ICT Robotic Cluster. The second one is Maritime Cluster. The third one is Automotive Cluster. And the next one, the fourth one, is Creative Industry Cluster. So we have 4 clusters of Technopark. And every cluster have already produced, and some of them already mass product, and we can buy it in the market, like Gesit as an electric scooter that is already mass product, and we can buy from the market. Ladies and gentlemen, so through this conference, I hope we can share our invention, our innovation, and also development of technology, especially in the artificial intelligence and its application field. And again, I would like to thanks to distinguished speakers, also ISITIA committee, the head of Department of Electrical Engineering, Pak Dedet, the Dean of Faculty of Intelligent Information and Electrical Engineering, and all committee, all person that already joined together, so this conference can be handled in a good way. So happy conference and networking. Enjoy ISITIA. See you in the next ISITIA 2022. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Professor Muhammad Azhari from ITS. We will continue to the next agenda, which is the keynote speeches for today. This afternoon, we will have Dr. Insinyur Ahmad Afandi from Department of Electrical Engineering ITS as the moderator. And for information, each keynote speech will have 30 minutes for presentation part and 15 minutes for Q&A or question and answer part. The audience can ask the question via chat Zoom or YouTube comment section, or maybe use the raise hand feature during the Q&A session. So, ladies and gentlemen, please welcome for all speakers and moderator, Professor Wolfgang Poch, Dr. Denny Pujianto, and Dr. Insinyur Ahmad Afandi. Time is yours.
Thank you, Ms. Aulia. Good afternoon, good morning to one and all present participants, respected Professor Azhari, Rector of ITS, Dr. Ketut Edi Purnama, Dean of Electrical Technology and Intelligent Informatics. Welcome to ISITIA 2021 conference for our keynote speakers, Professor Wolfgang Poch, from Graz University, Technical University, Dr. Denny Pujianto from Imperial College of London, Professor Xinghua Yu from National Sun Yat-sen University, and Dr. Adi Dharma. Distinguished guest speakers, ladies and gentlemen, this occasion we have representative from Europe and Asia, about 77 participants, speakers and participants. So for this session, we will continue to and discuss with the keynote speeches will be delivered from Professor Wolfgang Boss and Dr. Dani Pujianto. Good afternoon, good morning, Professor Wolfgang Boss. Yeah, he is the head of the Institute of Microwave and Photonic Engineering. This session, he will present trend in microwave front-end technologies. I think the time is yours for 30-minute presentation, and then we'll continue with the question and answer for 15 minutes. Please.
Thank you very much, Professor Fendi, for the nice introduction. First of all, let me thank the organizers for the invitation. It is a real honor for me having the opportunity to speaking to you, and welcome and good afternoon. I will share my screen. Good. I assume that you can see the screen, and my talk today is about trends in microwave front-end technologies. Let me see if I can. Okay, here you can see the outline of the talk. First, I talk about macro trends, the application space, specifically in the 5G area, and also some technological challenges we are facing. Then a few words about the semiconductors of the future, the technology mix I can see, and where the developments go, mainly silicon and gallium nitride. And then I give you a few examples of front-end technologies, mainly the passive components that move towards higher frequencies, the higher integration technologies, filters and antennas, some innovative printing technologies, metamaterials, and an application of a phased array antenna. Now, just looking globally at the global internet traffic, and if we look back to the year 1992, the global traffic was 100 gigabytes per day. Only 5 years later, in 1997, it was 100 gigabytes per hour already. And 5 years later, it was 100 gigabytes per second. And so on. 2007, it was 2000 gigabytes. 17, it was almost 50,000 gigabytes per second. And this year, it is predicted still 150,000 gigabytes per second. And we could see in the Corona crisis that internet and data traffic is essential and crucial. Now, on the right-hand graphic, you can see this exponential growth. So it is not linear, it is still exponential. And you can see normalized to the year 2010 with 1. We had in the year 2020, we have roughly 100 times more data traffic. This is mobile data traffic. And if we go further, in the year 2027, it is 1,000 times larger, the data traffic, compared to the year 2010. But it is not only the data traffic that is increasing, it is also the number of devices. And Cisco predicted 500 billion devices to be connected via the internet by the year 2030. So the message here is data traffic is still increasing significantly, and also the number of connected devices. Now, looking into the application space, and I take here as an example only the 5G application space, which is quite large. It is we see very different applications here. On one hand, you might know this triangle, by the way, was published by the ITU. On one hand, we have this machine type of communication. This is machine to machine, device to device, sensor to sensor. The data rates are rather low, but the sensors and the front ends are low power, low cost, a lot of different devices that are connected to each other. The keywords here are smart city or smart home, smart building. Maybe the smart grid as well for the in conjunction with the smart cities. Then on the other hand, we have this enhanced mobile broadband communication, and that is characterized by very high data rates. Here we are talking about gigabytes per second. We are streaming videos, high definition videos. We are organizing conferences like this, where we need a lot of very high data rates. And then on the third corner of this triangle, we have the ultra reliable and low latency communication. Here, the data rates are low again, but the important bit is that I get the information when I need it. I can rely that I get this information and I get it without any delay. So I know that within milliseconds, I will get the information I need. This is very important for mission critical applications, for emergency applications, for example, or for example, for self-driving cars. When the car needs to brake, it needs to brake now and not in a few seconds. So this is low latency applications. And when you see all these different kinds of applications all together, what is in common? In common is that all of them require low power. And secondly, I would say 99% is wireless. So it is not a wired connection, it is a wireless connection. This means that we need front ends. We need low power front ends for most of these applications. Now, what are the challenges in the future for this communication, but also for the sensor systems? First of all, as I already mentioned, it is low power consumption, but also the devices become smaller and smaller. So important is that they are miniaturized, and I need a high level of integration. Because we need low power consumption, there must be a highly integrated power management in the system. As already mentioned, the data rates are increasing. Higher data rates demand higher frequencies. And when we move towards higher frequencies and millimeter waves, then beam steering becomes more and more important, specifically also for mobile devices, not only for the base stations. We will require adaptive integrated filters and antennas. And the last point not to forget is the interoperability of the systems. We are facing more and more communication and sensor systems that operate next to each other, and they have to basically not to disturb, not to interfere with each other. So robustness, electromagnetic compatibility is becoming more and more important. A keyword is dependable systems. Now, these are the challenges. And now let me move on and talk a little bit about the semiconductors that are available. there are many different semiconductor technologies, and I mention only the three groups here. One is the silicon, CMOS and BiCMOS group, and this is suitable for highly complex integrated micro integrated circuits, also capable of operating at millimeter waves. They are suitable for fully integrated front ends. You can integrate the antenna, you can do the digital part, the baseband part, but also the microwave part on a single chip. And you can also think about additional technologies such as MEMS, which enable software-defined radios or other quite novel solutions and architectures. Then there is gallium arsenide technology. This is a niche technology and not suitable for very high volumes. Silicon is suitable for millions of devices. Gallium arsenide is suitable for hundred thousands of devices. However, gallium arsenide is a highly consistent and high yielding technologies for millimeter waves, and it is low cost, in fact, for moderate volumes. And quite often it is the enabler for new applications. If you look into the high volume markets of today, like the handset market, the point-to-point data link market, or the automotive radar market, all of these applications started off with gallium arsenide technology. And only when the volume picked up and the market developed, then the technology, the semiconductor technology, moved towards silicon. And then we have a rather new technology, the wide bandgap technology, that was developed in the last 20 to 30 years. And it is mainly for high power microwave applications, replacing TWTs or the LDMOS in base stations. It is suitable for broadband power applications, and it offers overall system benefits because of the high power density. The size is smaller, efficiency is higher. Cost is still an issue because wide bandgap devices are costly, but they offer high bandwidth as well. Now, here is a rather old slide from Huawei, 2016, but it shows roughly where these technologies are used. On the x-axis, you see the frequency, and on the y-axis, the output power or performance. And you can see for lower output powers and lower frequencies, RF CMOS is quite useful, but RF CMOS already goes up beyond 100 gigahertz. We have devices in CMOS with an FP of 700 gigahertz already available. And then if you need higher performance, then the silicon germanium BiCMOS technology, also based on silicon, is available and covers the whole frequency range up to, I would say, a half-watt output power, in that order. If you require more output power, gallium arsenide technology really is the best technology. And at the top, you can see gallium nitride for the high power applications, but also gallium nitride is capable of covering a very wide frequency range. For the very high frequencies, indium phosphide technology is available, or gallium arsenide MHEMT, metamorphic HEMT technologies are available as well. But you can see that the gallium arsenide technology here is squeezed from both sides. From the bottom, the silicon technology is squeezing into the applications, and from the top, gallium nitride is squeezing. So eventually, gallium arsenide will disappear, but I think it will take another 10 years, really, until gallium arsenide disappears. Now, here you can see how the technology, semiconductor technology, is changing for, or is distributed for power amplifiers. On one hand here, it is for lower frequencies, The blue and the red dots are silicon technology. The orange and green is gallium nitride, in orange and green in gallium arsenide. And you can see for millimeter waves down here, gallium arsenide is still used quite a bit. On the left-hand side, you can see the so-called silicon on isolator technology, SOI technology. These are engineered substrates and customized substrates. One provider is Soitec, and you can see that silicon covers the entire front end, the entire chain. So it starts off with the digital part on the transceiver, the power amplifier, LNA, the antenna switch. So basically everything can be covered by silicon as long as it is low power. When we need high output power, then gallium nitride kicks in. Here is another example from Yole. This is about 2 years old, a marketing study on the automotive radar. And automotive radar means more than just the front-looking radar. In a Tesla car, for example, there are already 7 front-looking radar devices built in. And we have rear-looking devices, we have side-looking devices. So there are many sensors built into the car, and you can see the list here of the different sensor systems. However, there is a big change going on in the car radar and car radar sensor market, and you can see the technology change over the next years. Initially, it was gallium arsenide years back. This is in the year 2000 and before. The first car radars have been built in gallium arsenide with GaN diodes, in fact. But nowadays, mainly it is silicon germanium. But you can see that already today, some of them move towards CMOS devices. And by the year 2025, half of the market is in CMOS. This is an incredible growth for the CMOS, and overall growth, of course, of 25% average growth per year. Many companies, or every company, is already working on CMOS integrated radar sensors, and there the entire radar is on a single chip. An interesting study did Skyworks, and this is a study of again the technology, and the question was which technology is good for a point-to-point data link. And here we have to specify, it is very specific here. First of all, it's a millimeter wave data link, and it is a data link with line of sight 300 meters. And then they were calculating the total power consumption per beam and the beam forming array independence of the number of sub-arrays or the number of radiating elements. And if you have only a few elements available, such as a 4x4 matrix, 16, then in order to have a good communication, you need gallium nitride devices. You need 25 dBm power at every element to cover the data link. The beam is rather wide. This is the dotted line here, and to the right-hand side, you can see the beam width. It is in the order of 20 to 24, 25 degrees. Now, when you increase the number of elements, then you need less power radiating per element. And you can, for example, realize the system in gallium arsenide, or here in SOI silicon. This is silicon germanium by CMOS, or you can do it even in CMOS, but CMOS delivers less power, so you need 128 or 256 elements. And you can see in terms of power consumption and beam width, there is a sweet spot, and this is its SOI. So for this application, it's quite interesting that a silicon by CMOS technology is the best technology here, and it's not gallium nitride. On the left-hand side, you can see a spider diagram of the different technologies. For example, you can see 45 nanometer SOI in green. This is suitable for very high volumes, high FT, or gallium nitride in purple, where you can see this is suitable for higher powers. So depending on the application, really one needs to select the right silicon or gallium nitride is the right semiconductor technology. Good. Now let's move on and give some examples of front-end technologies of the future and where the trend goes. First of all, if we look into a smart mobile phone of today, most of the smart mobile phones have several antennas or multiple antennas built in. So we have a primary antenna. Quite often we have a diversity antenna, and then we have other antennas for the GPS system or for the Wi-Fi system. And we have multiple channels, receive and transmit channels. And this means we need a large switch, and we need many diplexers and filters here. The amplifier, we don't need so many amplifiers because the amplifiers today can be built broadband. So they can cover a wide bandwidth, but not the filters, not the diplexers, and not the switches. This means in the future, for not only for the mobile handsets, but also for the watches, for the smart watches or any other mobile devices, we see that the number of active parts, in fact, of the amplifiers is reduced. However, the number of switches, the number of filters, the number of diplexers, antennas, the number of the passive components, and the tuning components is increasing. So this is certainly one trend we have to consider, that we have to learn how to integrate this large number of passive devices. So if you stay for a moment for the to the mobile phones and the millimeter waves, this is from Yole again, a market review, pretty new, 2 years old or 1 year old, and you can see that 5G mobile phones will be available and are already available. We are in the year 2022. However, the millimeter waves, this is the purple one here, is only implemented in the mobile phones very slowly. This is the purple one. And even in the year 2025, the portion of mobile phones that are capable of communicating in the millimeter wave range is very small. However, it is a growing market. The average growth rate is about 64% for the millimeter wave technology. So this is an important fact as well. Now, if we look now into a typical microwave front end of today, what do we see? We see highly integrated circuits, and the companies and the governments have put immense money into the development of integrated circuits and semiconductor technologies, billions in the last 20 to 30 years. And the result is that we can get highly integrated millimeter wave front ends on a single chip for $1 to $5 already, if the volume is high. So if the volume is in the millions, the chip is very is less expensive. So it is in the order of a few dollars. However, if we look into the interconnecting technologies, and if we use, for example, a SMT connector that is capable of millimeter wave, 67 gigahertz, depending on the quality, it costs already $15 to $50. And in case, I mean, here you can see a distribution network of a phased array antenna, and you see all these connectors here, and you can imagine how expensive this is. And if you look into the antenna and the integrated, not an integrated, but a fully assembled antenna for millimeter waves costs you a few hundred, even a few $1,000s. So what does that tell us? Only if we want to build in the future millimeter wave front ends, only when we optimize the transitions, also if we can integrate passive components, if we can integrate filters and antennas, and if we optimize these technologies, only then they can enable the market and leverage the integration capabilities of cost-effective silicon semiconductors. This means we need to put in a lot of effort in the future to into the interconnection technologies, into technologies of filter and antenna integration, really to have low-cost, high-performance millimeter wave front ends in the future. Here is an example of an automotive radar and the cost breakdown. But if you take a mobile phone or any other mobile devices, it looks the same. And you can see here the four-way switch and the radar sensor is only 8% of the cost. And 73% of the cost is in the main board, is in the integration. And that needs to be reduced. So the research effort should go into the integration technologies, into the board design, into the design of the filters and the antennas. And what is the solution now? What to this problem? What can we do? And it is, on one hand, we have interesting technologies available. We have quite some advances in the future today in the PCB design, in LTCC technologies, multi-layer integration technologies. Then we have additive manufacturing advances. So we can 3D print circuit boards, for example. We have big advantages in the semiconductor technology. We have very high performing CMOS technologies. And we have also in the design of planar antennas and filters, we have advances specifically using electromagnetic simulations. So, and we have to merge these technologies. We have to do multidisciplinary research in all these areas, really to address the 5G and 6G and automotive radar requirements. So I would really suggest and tell people to intensify the research in these millimeter wave active arrays. And I would like to show you a few examples here. One is this higher integration by embedding. So you can see that active parts like this chip is embedded in a multi-layer PCBs. The antenna is embedded. We have horn antennas, we have patch antennas. This is one example where the technology goes. I do a little bit faster because the time is running out here. Also, there is a big trend into combining functionalities. This means one component can have different functions. And one example is a filter. And this is a typical filter that is three coupled resonators. These resonators are capacitively coupled. Now, an antenna is a resonator as well. And we could use, for example, the last resonator here at the same time as the antenna. So what we get is a filtering antenna. So we see here the radiation diagram and also the filter function of this antenna. And this is not a new idea, but there you can see a lot of different designs that are published at the moment. This is work at my institute here. This is a Ka band filtering antenna of a stacked phased array, and you can see the filter characteristic of this phased array. It is a very small profile, low profile design. This is another example of a filtering antenna, and in fact, it is a patch in the center, the patch that is fed, that is the active patch in the center, and then outside you have 4 other patches that are capacitively coupled, and these patches are resonators. So, and in this way, this antenna is, first of all, the antenna radiation pattern is focused to one side, and at the same time it is a filter because of these 4 coupled 4 radiators. It's a very nice example here for a quite broadband antenna. You can also, now moving away a little bit from the antennas, but to the filters, one can design dual mode or triple mode filters, which means in one resonator, we have different modes of resonating modes. And if we couple these modes, then we can realize higher performing filters with more resonating modes, but only one resonator. So here is a quite nice example. The overall, this is a patch, and that patch can resonate in 2 different modes. And by cutting the corner here, we couple these 2 modes. So although we have only one resonating structure, we have 2 modes, and we have a dual mode filter with quite nice performance. In addition, this is tunable in the center. Good. So now moving away from these filtenas, in the last years, 3D printing is just used in every technology, and for implants in the medical area, for mechanical parts, in engines, for all different kinds, even for food, and also in the microwave area. And this is quite a nice example where an antenna at 140 gigahertz and 300 gigahertz was realized in metal, but also in plastic. So we can print metal, we can print plastic, and we even can print ceramic. And a lot of research is going on in this area with quite promising results. When you arrange periodic structures, basically you have a periodic structure and you have, for example, resonators that you arrange in a periodic way, then this material can be called a metamaterial, and it has very specific properties for wave propagation. And in this case, one idea is to realize a planar lens that can focus the electromagnetic wave. And the lens is built of a periodic structure of resonators. Now you can realize these resonators in all different kinds, and these are the first prototypes here, where a ring resonator like this was arranged to form this lens. And the application for these lenses are a lot. One application, for example, could be that when you have an integrated antenna and then you place, for example, a horn antenna to this integrated circuit, then to radiate, then you can see in the ideal case, this is in the upper stream, everything works fine and the wave moves through the antennas. Now, quite often there is a little air gap in between, so between the integrated antenna and the little horn antenna. And this air gap totally destroys the wave propagation. And you can see it in the center that there is no focusing anymore. However, if you place a planar lens, and this is just, it could be, you know, a planar meta material there, it helps focusing again, and you can see that the air gap has no effect anymore. So we have a focused wave that goes into the horn antenna. This is only one thing. You can do other stuff as well in the area of electromagnetic compatibility to either focus a beam or defocus, in fact, a beam through metamaterials. And this is the last example. In fact, this is the research work of Pras Mukti, who is with you at the moment. And we are working on so-called observation radars, and also radars that, for example, detect birds and stop the windmills, so to protect bird life. And Pras was using very advanced technology here to build the prototype of a phased array antenna, and first measurements are already available, and he's preparing also a publication on this. So this is only one example I wanted to show you how you can use modern and novel technologies for phased arrays. Now, coming to the conclusion. We have billions of devices that are wirelessly interconnected, and we have a steadily increasing data rate. Now, this increasing data rate requires wider bandwidth, they require higher frequency bands, and beamforming and MIMO is also required at higher frequencies. So we need to look into beamforming, we need to look into these integrated front ends and phased array antennas. For the semiconductors, I can see mainly silicon and gallium nitride in the future. And if we look into the trends of front-end technologies, we have more passive components. We need low-cost integration technologies. We have combined functionalities like the Filtena I have shown you, and we have new manufacturing technologies. And with these new manufacturing technologies, we can build new materials. For example, metamaterials, but we can include ferrites as well in these materials. And I didn't mention this, but there is a trend towards all digital front ends, at least at lower frequencies, you can digitalize everything. So, and that concludes my talk. And I'm happy to answer any questions.
Thank you, Professor Wolfgang Boss. And we have about 10 minutes to question and answer. Please, if you have some question, please raise hand.
Shall I stop sharing so I can see the chat as well?
Yes, please.
Okay, good.
Please, if you have any question concerning the application of front-end technology, which is used in beyond 5G technology. Prof. Kamantio, maybe.
Okay, I would like to have a question then. So good morning, Professor Bosch.
Good morning.
Yeah, it's great to see you here. Thank you for giving us a speech that was very interesting and useful for us here. I have only one question, and it is with regards to the last point in your conclusions, which is that right now there is a trend towards all digital front end. With regards to that, will there be any change, and what kind of change that will be happening in the research direction, especially in the areas of RF engineering, when everything is going digital? Thank you.
I had a few slides prepared on the digital front end, but because of the time, I couldn't show them. Now, what I'm talking here is there is quite an interesting work in at the Ferdinand Braun Institute in Berlin, and they could demonstrate a switching amplifier, basically an amplifier that only turns on and off with very high efficiency, and typically after a switching amplifier you need quite an advanced filter to filter your the signal again to have to bring it back to the analog system, to the analog world. And they could prove, and they could show that this filter can be realized in a very simple way. And this is new, because in the past we had very complex filters, very high Q filters, and they could show that it's not really required. However, this works only for, I would say, sub 1 gigahertz, because you need very fast switching devices. So I would say what I could see there is for low frequencies, the modulation can be done in the digital domain, the amplification can be done in the digital domain, but you still need the front end. You need a filter and you need the antenna, and you need antenna switch. So this is, I think, the minimum that will stay in the analog world. However, as I said, this works only for low frequencies. I can see this for below 1 gigahertz, maybe 2 gigahertz, but not higher, because they were already using a technology, a gallium nitride technology with an FT of, I think, 30 gigahertz. So I do not see digital front ends for millimeter waves. For millimeter waves, and I'm talking, higher than 6 gigahertz, it is still the analog, the front end. And I also think the beam steering is going to be hybrid. A fully digital beam steering, and to digitalize, the signals from every antenna element, and then do the beam steering in the digital domain, is very power consumption. It has a very high power consumption, because you need a lot of computing power. And that is why I think it's going to be a hybrid combination, that we have some analog beam steering like phase shifters, and then for sub arrays, and then the sub arrays, the signals from the sub arrays are then digitalized and then in the digital domain processed. So it's going to be hybrid because of cost reason and power consumption.
Okay, thank you.
Thank you, Prof. Wolfgang. Is there any question? While waiting for the question, another question. Is that mean that below 1 gigahertz, the SDR will be dominant in the future?
Yes, I think so. I think so, yes.
So for the country like Indonesia, for example, for the purpose of education, shall we focus on SDR for realizing the telecommunication system, or you prefer to recommend the RF over 3 or 6 gigahertz?
I think for the, as I said, for the lower frequencies, the SDR have a lot of advantages, because they can, they can grow with advances in the system. And if you have hardware for higher frequencies, then quite often you're limited by the hardware. The performance is limited by the hardware. Whereas for SDR, I think you are more flexible. It's hard to say, and it depends on the application as well. If it is pure communication, I don't, for example, in the radar side, I don't see the SDR. I see rather the hardware implementation. For communications in certain applications, I think SDR is the way to go.
Okay, thank you. Is there any question? Maybe from the YouTube? Is there any? No? Or from chat? We didn't see the question. So if there is no question, we can conclude this session. Thank you very much, Professor Wolfgang. We hope you can visit us in the next time, if everything is possible to have traveling around the world. And we continue, and we give applause for Professor Wolfgang before we continue to the next our keynote speaker, Professor Dr. Dani Pujianto. Please, Dr. Dani Pujianto. He is a research fellow from Imperial College London in Department of Electrical and Electronics and Engineering. He will present this time, role and value of smart electric vehicle studies in Great Britain. Please, yours, Dr. Dani.
Thank you very much, Mr. Chairman, and good afternoon, everyone. Just before I start, I would like also to say thank you for having me here in the conference. And it's good to see some of the my teachers also here before. I was studying in ITES in 1991 to 1996. Professor Asari, Professor Dr. Mujiono, Professor Hendra Kusuma, it gives a special warm feeling that I can see you again, and hopefully next time I will be able to visit the campus when everything is already sorted out. So again, the title. Let me share my screen now. So I assume that you can see my screen here. So as mentioned that my presentation today is about the role and value of smart electric vehicles, and especially the studies in Great Britain. Here first. And the content of my presentation first is what I will start with what is actually the main driver for having electric vehicles, and few things about this electric vehicles technologies, the cost of batteries, charging, energy consumption, and the challenges for the system integration of these electric vehicles. And then why the people in Great Britain think that, and also across the world, and think that there is a need to go towards more smart electric vehicles rather than just a dumb technology that just plug and play there. The modeling approach that we have carried out, and a number of case studies and the key findings, and some also I will discuss with some of the trial that has been conducted in the UK, and of course the summary of this presentation.
Dr. Dani, can you make a full presentation for your presentation? Because we still see the next animation. Yeah.
Okay, sorry.
Duplicate slideshow.
Is it that you can see my screen now?
Yeah.
Okay.
Yeah.
Okay, so the main driver for these electric vehicles and the shift from the petrol to electric vehicle is the climate change. And we heard last week horrible news that in Western Europe, Germany, Netherlands, Belgium, there were a number of floodings there, quite a severe one. And this is a picture that the left picture here is the aerial view for this Erfstadt Blossoms kind of village town before the flooding, and then after the flooding. And you can see a lot of destructions happening there, and more than 180 people die because of this. And this not only happens in Germany, but also happens in other Western Europe. And a few days before that, it's also there is the part of London received a month of rain in one day. So you can see that it's a flooding as well in here. So what the experts say that this is caused by the global heating, which causes more water to evaporate, increasing the amount of annual rain and snow. And the warmer atmosphere is also hold more moisture, which also increase the intensity of rainfall. And then the intense rainfall also leads to flooding. Just bear in mind that these cities, and so London's, they normally already have kind of the flood defense, but of course the capacity will not be sufficient if it is the rainfall, for example, like this a month of rain just poured down in just in one day. And this morning we also got the news, and this also happening in China, in central China, in Henan province, that is the heaviest rain in 1,000 years, and the frequency becomes more often. And that's not only flooding; is the issue. There also increased drought and also forest fires, especially also in the US, Australia, and all are about the climate change, about the temperatures increases and the global heating things. And the primary cause for that is the increased carbon dioxide or greenhouse gas in our atmosphere. And what happened in the UK is that the transport sectors actually contribute about 30% of the UK greenhouse gas end user emissions. But there have been little reductions in 30 years, and you can see that this diagram shows the greenhouse gas emissions from the transport sectors in the UK, but the end user or the buy source, and they are relatively kind of flat. So there is a radical change that need to be done to reduce the emissions to tackle with this the climate change issue. So in last December, the Climate Change Committee in the UK issued this UK Path to Net Zero. This is a 6th carbon budget. And the left diagram here shows the carbon intensity, grams CO2 per kilowatt hour of energy use. That has to be, that we already see some reductions in the past 10 years from around 500 gram CO2 per kilowatt hours is driven by the use of a lot of fossil fuels, down to 200 because the already increased significant capacity of the renewable energy in the UK electricity mix, but this has to be down further to net zero in 2050. So it's a very big challenge, and also it's a lot of shift in how we plan and operate the energy system. And to meet net zero, the emission must fall not only in the electricity, but in all sectors, including the transport, buildings, manufacturing, construction, agriculture, waste, and so on. So this has to be down quite significantly. And you can see that here is the transport sectors, which is relatively the same at this moment now. This has to go to the zero in a faster rate in 30 years. So how to do that? There are a few recommendations. One is from the Climate Assembly recommendation, is that to ban on the sale of new petrol, diesel, and hybrid cars by 2035, and then a reduction in the amount that we use cars by an average of 2 to 5% per decade. The recommendation from the CCC is that this 2030, 2035 will be the switch over date for the EV, so moving towards all the electric vehicles, and up to 5 to 11% of travel distance from the cars switch to the alternative modes of transport like rail, tram, and so on. So this slide shows that the left diagram here shows the carbon dioxide emissions per kilometers driven per cars, and then there are 3 countries used for these illustrative examples, the UK, the US, and China. And this is the current kind of situations. And the number of technologies for the electric vehicles from the BMW, Nissan, and also the Tesla. And this is compared against the best-selling petrol car emissions. And we can see that with using, and of course, the emission from the electric vehicles here is driven by the electricity mix and how this electricity is supplied in different countries. For example, like in China, there may be primarily still a lot of gas or coal plants. So the emission, the carbon emission intensity there is still relatively higher compared to the other countries like UK and US. But this shows that the best selling petrol car emission is around 100 gram CO2 per kilometers, while at this moment with the UK, the best technology perhaps is that it is maybe around 40 grams CO2 per kilometers. And in 2040, this will be reduced further, given that there will be a lot of shift from the fossil fuels, from the unabated fuel generation here. This is the diagram here show how the electricity mix evolve from the 2020 to 2050, and we can see that a lot of reductions from using of the fossil fuel generation unabated towards the renewables, more than 100 gigawatt renewables by 2050. Currently, we only have around 14 gigawatt onshore and 10 gigawatt offshore wind, and 13.5 gigawatt of PV. But that will increase significantly to 100 gigawatt rest by 2050. And also other form of the low carbon generations like nuclear or hydrogen power generation also will be used. So as you can see that the emission factors, which is maybe around 2035, that most of the electricity sectors, electricity generation in the UK will be fully decarbonized by then. But another key point for this graph is also that the electricity demand increases significantly by 2.5 times higher than the current electricity demand, which is around 350 terawatt hour per year. And this may increase to around 700, just a bit less than 800 terawatt hours, depending on the assumption that we use here. But this significantly shows some big challenges on how the electricity infrastructures will need to be planned and operated in the futures. Another point is that the decarbonization of these transport sectors here, this has to be aligned with the decarbonization of electricity. That cannot be done sparingly. So you shouldn't have electric vehicles without decarbonizing the electricity sectors. And I think this is a very important message, because if not, then it may increase the emissions level actually. And also other sectors, not only electricity, but also like heat, which also contribute around 30% of the UK emissions. The next slide is, now with the renewables, some people said that, okay, the renewables now is quite expensive, but it is not the case any longer. You can see there, this is the levelized cost of electricity from different low carbon technologies compiled by IRENA. There's a report, renewable power generation cost in 2018 for different technologies. But if you focus on this, the main technology like the solar PV and offshore wind, which are the main technologies in the UK for low carbon technologies, that the cost is actually reduced very significantly. So from around $0.37 US per kilowatt hours in 2010 towards only, this is 8.5 cents per kilowatt hours in 2018, and this goes further down because of the improvement in the technology. Offshore wind also reduced significantly, and it's driven primarily also by the deployment of those technology, which then reduce the financial risk and increase the already know-how on how to install those. So that's reduce the risk, and that reduce the cost. So then this will be then quite comparable with the cost of the electricity from other sectors. So there is an economic case also for this for the renewables. Now with back to the electric mobility, it's not only about cars, but it's also about the motorcycles. I know that the ITS has developed with the electric motorcycles. In the UK, that's motorcycle is not used very much here, possibly because of the weather. It's raining quite a lot here, so maybe it's not ideal, and it's also windy. But there is also electric, the hoverboard, for example, or just scooters. But the emerging technologies for this electric vehicle is about the battery. So battery is the key technology for this. And then the research in the Energy Future Labs, for example, at Imperial, indicates that, for example, using the advanced cooling system can lead to 10 to 15% range increase, to 100% longer lifetime, and 15 to 20% cost reductions. So this required maybe a radical change on how the battery should be designed, and also the technology. There is also quite a lot of work in this area. Another key area is about how to do more efficient driving, and also the automations. So the optimal electric vehicle control management system in order to reduce the energy usage, and that will lead to the longer lifetime of the battery. It's also improved the security and comfort, and then maybe you already have heard about the number of trials with using the autonomous fleets. So battery is with the EV, main concern is about battery, because the batteries makes up a third of the cost of the electric vehicles. But the good news is that the battery costs continue to fall, and also this will actually trigger more demand for the electric vehicles. So this is the data compiled by Bloomberg from 2010 to 20 and then projected to 2030. And you can observe here that in 2010 that the cost of the batteries it's around $1,000 per kilowatt hours, but this goes around almost 350 here to 2015, and this is the actual data price, and then this is the estimated range, and I think this is around, it's quite right, it's around $200 per kilowatt hour at this moment, but it is expected to be less than $100 in 2030, in 10 years time. And this increases also the demand of the EV. So with the massive mass production scale of the battery, then the cost can also be reduced. Now, charging the electric vehicles, there are a number of types, charger rating, and this has to be taken into consideration seriously when we design the energy system with the electric vehicles. So the lowest one here is just the regular electricity socket, 13 amps. It's a slow charging, it's a AC normally, it's a 3 kilowatt. Now, in the UK, the house, normally there are three. They are supplied by a 60 amp, 80 amp, or 100 amps. So it's about the 100 amps. So you can have almost 22 kVA, 22 kVA, yeah, for us. So it's a 3 kilowatt is not a problem here. And maybe also normally in Europe, in Western Europe, that's also quite big. But in Indonesia, this will be quite challenging. This will take for time to charge for 10 kilowatt hours battery is around 3 hours 20 minutes. For 30 kilowatts hour battery is 10 hours. And then we have a bigger charger rating here that reduce the charging time, 3.7 and 7.4. I think that these are the typical charger in the UK. For 7.4, it's only 1.5 hours basically. This is a single phase. But this goes to the mall and office. They can use 3-phase chargers, which is a bigger rating. And for the stations, which is dedicated to charge the EV, it can go up to 50 kilowatt or 120 kilowatt with the DC chargers. And this reduces significantly the time to charge the battery to 5 minutes. So this table shows how much energy needed for 100 kilometers, like travel distance. So it's typical, it's around 17 to 18 kilowatt hour per 100 kilometers. If it is good, then it is 15 to 16. If it is an excellent, then it's 12 to 40. So the better, then it becomes the lower numbers, of course. And in the UK, that on average, people travel around 1 hour travel per day. And this can be around, I think it may be a bit offer estimate here, is maybe 50 to 80 kilometers per day. And if it is converted to the energy, it's maybe around 8 to 13 kilowatt hours per day that need to be put into the EV. And for the residential, it's just 1.5, 3.5 hours charging. I think the number of travel is also become much less, especially in the previous 1.5 years because of this pandemic situation. For the fast charging, this only takes 5 to 30 minutes. So it goes to the mall, shopping centers, it's just plug it there, and then that's in 30 minutes after finish shopping, then it's already fully charged. Compared with the gasoline engine, the gasoline engine require about 5.5 liter per 100 kilometers. This 1 liter of the gasolines contain maybe around 9 kilowatt hours of energy. So it's around 50 kilowatt hour per energy per 100 kilometers. So from the energy perspective, that the electric vehicle is much more efficient. Now what we have done is that, and this has been quite a while back, that we take into consideration the data from the Department for Transport with the 67 million journey and all with the starting time, end time, and then the travel distance and number of journey per year. And using the data that we then develop kind of a profiles of the load of the electric vehicles. And you can see that there's the profile here is that when people from homes arrive to the office, they plug their vehicles, this increase the electricity load at this time, and then it goes down. And when people back home, then they plug it again, and it will increase the electricity load associated with the EV, and then it goes down again. But the problem is that this big load is coincide with other electricity load, which then means that it increases quite a lot the electricity peak demand of the system. So this is the study for the 2030. Currently, we have around 60 gigawatt peak demand in the UK electricity grid, and if there is a EV plus also the use of the heat pump, which is during the winter, then the EV, the contribution of the EV itself is already increased 25 gigawatt in the electricity demand, and that's around 40% of current kind of the 60 gigawatt, the previous 60 gigawatt of peak demand in the UK. And this is massive, and this will require the generation, transmission, distribution to be designed to cope with this increase in the electricity demand. The problem is that this, as you can see, that the usage of here is, in terms of the energy, is not large. So, but the increase in the peak demand is significant. So this implies that the assets that need to be built to cope with this increase in the electricity peak demand will be underutilized. The utilization factor will be lower than what we do if we do nothing. So that's we need to be smart to deal with that issue. And then in the beginning, people think about how to make it the demand flatten. So and then the good thing with the EV is that if you notice in the previous slides that it's only about 1 hour driving or 1 hour travels. So it means that another 23 hours that the cars will be stationary, connected to the grid, but will be stationary, will be there. So it means that the load can be shifted quite flexibly. And the idea is to flatten the peak demand in order not to increase the electricity. But then we realized that this is not only about electricity peak demand. The EV challenge here is also about, and also maybe also to provide the opportunity, because the future electricity mix will be mostly coming from the renewables. So then, when there is a increase in the wind power, for example, then there may be a need to increase the electricity load to be able to absorb that wind, because if not, then the wind will be curtailed. But if it is increasing the load associated with this EV, that this will require additional capacity at the distribution, and also other generation transmission capacity that need to be built. So there is a conflict between the operation here. Let's try to optimize or to maximize the utilization of wind, renewable energy sources, with the capacity of the system, especially at the distribution. Now this the diagram shows how the system will evolve. Currently, that we got the fossil fuel generation, but in the future we will have a lot of wind, as I show on the previous slides. About 80% coming from the variable renewables, and then the rest will be from nuclear, from hydrogen, and so on. But currently, the energy flows coming from the generation, large-scale generation, through transmission, distribution, go to the end users. And all the flexibility and how the system design is that the generation will follow the load, because all the flexibility is in the generation. When we switch on our switch at home, we don't care when this electricity will come from. So the system has been designed to do that. But in the futures, wind will not follow whatever the users. Wind will do whatever it does. So and also with wind, with a lot of wind, then there will be a reduction in the capacity of the controllable generation, and that's why the flexibility from the generation side will be less, and that's why at the demand side, or also the storage, this will become very important, and EV is part of this. And in UK, that this has been realized that there is a potential opportunity for the electric vehicles to provide the grid support. So in terms of the energy, it is still, we envisage that in the future, in 2050, that there are a lot of energy will still come from large-scale plant like the offshore wind, and especially in North Sea, going towards transmission, distribution, and then users. But the demand will need to be flexible, and this flexibility will affect not only the distribution, transmission, but also how the generation will evolve in the future. So the smart EV, if we focus only on the smart EV, this can provide a number of type of flexibility. One is that it can be used to do energy arbitrage. So when wind blows, that charge it, because the electricity price becomes also lower. When there is no wind, then of course the system will use a peaking plan, and then this will increase the operation cost of the system, and then do not charge during that time. It can also do the peaking or backup capacity. So if it is if there is a scarcity in the systems because fault in big plants, for example, that the EV actually can also becomes like a generator at home, and it can supply the load at the generator at the home levels, in order to prevent not having this load shedding for this critical loads, especially with current situations, with the oxygen, for example, at the hospital and so on. The electricity, the reliability of electricity supply becomes quite important. System balancing is follow winds. It also can be used for network services. If the network is congested, it can be also used that the EV battery, if it is injected to the grid to reduce the congestion. It's also be controlled to reduce emissions by following the output of the low carbon energy for wind, PV, and so on, and maximize, of course, the self-consumption of the on-site generation like PV. Now, the challenge in here is that when we try to evaluate the value of the flexibility from the EV, this will require the consideration of the whole energy system. It's not only the electricity, not only distribution, but also all from the generation, supply, and transmission, but also not electricity also, but also the other energy factors. So what we have done is to do the whole energy system model. You can see it in here. Just in a nutshell, it is a large-scale or optimization problem, including containing all the energy system from the supply side, the generation, transmission, and also the distribution. It also involves not only electricity, but also heat demand, heat, because heat is 60% of the energy demand in the UK, and also need to be decarbonized along with the electricity and transport. And we also use model also the hydrogen system here, because the electrification and hydrogen, the use of the green gas to decarbonize the system. So it's not only the whole energy system here, but also the spatial granularity need to be taken into account. So the model considers a number of regions in the UK in here, and also take into account from the system adequacy problems from multi-years, because the system has to be planned to have a sufficient capacity to deal with the extreme events, for example, with peak demand, no wind, or low renewable output, and also ensure that the operation is efficient for the long term of seasonal up to the day ahead, but also take into account the reserve and response. And this is quite important because, as I mentioned earlier, that there will be a significant reduction in the flexibility in the generation side that need to be dealt with. I think this is just to show that we model from the street level here. This is the pre-analysis before we take into account, before we put it into the large-scale optimization problems. We created this to understand the impact of the increased electricity load at the distribution level for urban and rural system, and then we put it into the tool, taking into account the number of different technologies from demand side, flexible generation, network, storage, and there is also because the UK is quite isolated as an island here, so there is a important aspect of energy exchange, or also the ancillary service exchange with Europe that has been taken into account. Now, this is one of the studies for the value of the smart EV. And that depends on the, so this scenario is using the 2050 energy system scenario with the carbon target of 30 megaton CO2 per year. The counterfactual or the reference is that if there is no EV flexibility, and the analysis here consider number of cases with the smart EV 40% and smart EV 80%. In the system, all transport has been electrified. And we also carried out study with the functionality, with different functionality of EV, whether the EV can do only energy arbitrage or can do energy arbitrage with the frequency response, whether we apply the 50% of the vehicle to grid. So with the vehicle to grid is not only about the load shifting of the charging of EV, but it's because it has battery, so it can also inject back to the grid if needed to provide the ancillary service. So 50% and 100%, and we carried out with the 40% and 80% kind of penetration here. And we can see here that the results show that a significant benefit of EV. So the more functionality of EV we have, that the benefit is higher, and the benefit is in here is at the extreme case is around 8.5 billion per year, which is very, very, very significant. And this is associated, and the main benefits here are in the reduction in the electricity generation, because there is in the electricity generation investment cost, and also the reduction in the electricity network, and plus the sum of the OPEX. The OPEX is relatively small, given that most of the technology that we will use in the future will be based on the zero marginal cost generation like wind and PV, or even nuclear is relatively low marginal cost as well. There are some saving in the hydrogen, the CCS, and hydrogen CCS infrastructures that we can discuss it in next in future and more detail about that. So most of the values will be reduced in the CapEx, electricity generation, and networks, but currently there is no proper market frameworks to do that. So but there are already a number of trials to develop this market to incentivize the EV investors. Running out of time, and this is the impact of the smart EV in the context of this enables higher share of electricity production from renewables. If we say that there is no smart EV, this is no smart EV, then there's the wind that we can absorb is only 325 terawatt hours, but there's a significant amount of nuclear. Nuclear is firm low carbon generations here, but it's more expensive than wind, given the assumption taken in the study. But if we go to the very, let's say, go to the extreme case with the V2G, 100% V2G with the high EV penetration, then we can have half of the nuclear, and then increase the wind and also PV quite substantially there. So that's the reason why we have saving in the cost of the electricity generation, because we can utilize variable generation, which is a lower cost, but it is variable. And because of the carbon emission constraint, then if there is no flexibility in the system, then the model will need to use firm low carbon generation like nuclear. So this is just to show how the EV will behave, the smart EV will behave. So this is a 7 days in winter with 3 days during winter peak demand. As you can see that the electricity demand increased up to more than 200 gigawatt here, and there is no wind. The wind is in the blue one, very, very low wind, and also low solar. And during this period, then the demand is supplied mostly by the CCGT, and the EV is to be shifted from the the daytime to the early morning or late evening, in order to reduce the peak demand here. And the peak demand here is primarily driven by the use of heat. So this happens kind of quite consistently in these 3 days, because this mimics how the present traditional power system currently with the peaking generation and so on. So is that the rule of thumb is that just shift the EV to the off peak. But when we have a lot of wind here in this another 3 days, the wind coming up with big, then the EV charging then becomes irregular. This is to follow, and we can see here the patterns. For example, this actually try to follow wind. So this just to highlight my points earlier, that it's just not only to reduce the capacity, but also to have to optimize the operation of the system. And this is the utilization of EV and smart appliances here across seasons, so it's winter, spring, summer, and autumn. And we can see that this is used almost every day. So it's not only used once or few times in the year, but it's used every day. And this is driven not only by the capacity, as I mentioned, but it's also driven by the need to follow the renewable output. Of course, in the winter, the utilization is highest, but it's also we observe that this also applied in other seasons as well. And this is the load shift and the load shift of EV and smart appliances for the hours. So what does this diagram say is that for hour 1, for example, up to hour 6 in the morning, 7s, that it is likely that the EV load will be shifted to these hours. But from the model we observe that there are some variations on how much the EV load need to be changed. During the daytimes, it's also likely to be reduced, but again, the range is that there are some occasions that this actually needs to be increased during the daytime because of the wind, as I mentioned earlier. And during the evening peak, like 7 o'clock evening in the UK, then it's time to be reduced again. But what it tells us is that a static load shifting control strategy will not work in this case. It worked in the past, for example, that in the UK we have got economic 7, means that the heating is charged during the late evening or early morning time, because of there is a timer for that, and then the heat is released after that, and it is quite static. The timing is already fixed. With the EV, with the future energy system, we anticipate that this will not suitable. There is a need for more dynamic, more intelligent control frameworks that need to be developed in order to maximize the system benefit of the EVs. So just to kind of finish off with the trial here, so there are lots of number of trials. So there's already a convincing evidence from the studies about the benefit of EV, but of course we need to do some trial to understand it in a more practical way. So there are a number of trials here. That's a vehicle to grid, for example. Here you can go to this V2G hub. That's kind of summarize the V2G trials across UK, but also the world. And again, this is not only to use. This is just to maximize the value of the EV, not only to decarbonize, but also to the transporter, but also to support the electricity grid by providing ancillary services and then also frequency response, for example, energy arbitrage, and also the making it more resilient against some extreme events. And it is beyond not only cars, but also buses, for example, and here. So there's a bus to grid project. It's a world's largest V2G project in London. At the moment, there's a number of 28, if I'm not mistaken, bus, but the plan is to have 100 buses with this capability. So again, this is a V2G, so it's 2 directions. So the batteries can give back as well, take from the grid. And just to quote here that there are around 9,000 buses in London, and if those are fully electrified like this, that this theoretically can provide support more than 150,000 homes if needed, if there is a big outage in the electricity in the system, for example, or the scarcity in the supply. So just to summarize, so transport contributes to 30% UK emissions that need to be decarbonized via electrifications. It required strategic and coordinated planning with the electricity decarbonization. It cannot go just in silo. And the key challenge here is that there is a significant increase in the electricity demand and, of course, the system capacity requirement that need to be dealt with. But there's also provide the opportunity to improve the system flexibility by providing the grid services. And how to maximize the benefit of the smart EV is that we propose or we advocate the use of the whole system concept, not only from only the distribution to minimize the distribution reinforcement, but also looking the whole pictures. There are still many challenges to integrate EV. For example, with the commercial intelligent control frameworks, it is not still clear on how this should be done. Ideally, and then that's the reason why it's a lot of trials happening at this moment in the UK and in Europe. So yeah, so thank you for listening, and then welcome to any question you have. So
thank you, Dr. Semi. Please welcome for the question from the audience. If you have any question,
so
please raise.
Me, Dr. Fandi.
Okay, thank you, Prof. Imam. Please.
Yes, welcome, Dr. Dani Pujianto from UK. Yes, so this is very interesting because you discuss from the power generation until the loading, also included the electric vehicle. Now in UK already converted more and more from the conventional vehicle to be electric vehicle. What is the response of the UK society, UK people to receive the new technology? That's mean about electric vehicle in surrounding of them. Because maybe we need the new culture, move from the conventional technology to be the modern technology, the electricity. Thank you.
Thank you, Professor Imam. The response is very, very positive. Now, just from my personal experience in my neighborhood, and I mean just my neighbors, they already changed to electric vehicles, and the next neighbor is also planned to have electric vehicles to replace his old car. So the response is very, very good, and this is actually driven by that the government gives incentive, especially with the tax. So for the very low carbon emission like the electric vehicles, that they may not need to pay tax at this moment, and also there is also quite high cost for the fuel cost. So in the UK, the fuel cost is maybe around 2.5 times bigger compared to the fuel price in Indonesia, for example. It's very quite expensive because of the tax. And with the electricity, it is cheaper in terms of the operation cost, although they have to the capital is quite expensive. And there is also another maybe a social aspect associated with this, because people want to be shown as the environmental friendly, so they choose also this technology. I mean, there are also a lot of awareness about the impact of this emission from the transport, and then people in the UK, I think most of them, they are quite aware of that, and they choose to shift to the electric vehicles. So the response.
So maybe there is the funding from the government to the bus company. That means the conventional bus company to convert his buses to be the electricity cars like this?
Yeah, there are many fundings encouraging the companies to switch to electric. There are many trials as well. But of course, like what I just showed earlier with the bus to grid projects in London, for example, that has been also funded by the government. So yes, I think the role of the government here. Sorry.
Yeah. Okay.
Just would like to highlight that the role of the government is very critical in terms of incentivizing people to shift their, to this new technology.
Yeah, that means you can develop the new grids for support the electric vehicle like this, or develop the battery, which better? In this case.
So I didn't catch but in terms of the battery, yes, it is. There are a lot of technologies also. I think the number of different fronts of the research that has been addressed.
Oh, okay, yes.
Yeah, so there are many.
Because you just already mentioned about the grid. That means you spirit with the problem of the batteries.
Yeah. I mean, the batteries technology has been improved substantially in the past 10 years. As you can see, also the cost also becomes less, and there is also there are a number of technologies also at the horizon. For example, using the graphene. Manchester is at the front side of this the development of the graphene-based storage, for example, so the nanotechnology used there. So and also at Imperial we also, as I mentioned earlier, that there is research on designing the batteries, having a radical change on the design of the battery to improve this heat performance, or the cooling performance of the battery in order to prolong the lifetime and reduce the cost. Yeah, but on the grid side, and also the control side, there are still challenges on how to, for example, to understand, to give signals to the individual electric vehicles about the grid needs and how to do the commercial framework from the service from the national grid, for example, which require this service to the people. So there are a number of business model has been developed. There are a number of aggregators that then they contact the customers and then they aggregate the service and then sell it to the national grid. So that also are still in development at this moment.
That means UK, yeah, that means UK already changed all the transmission line configuration or distribution configuration to face the new demands. That means the electric vehicle like this.
So in terms of the infrastructures, I think they are not very much different at this moment. The issue is about the control, how the operators use it. But there is, for example, like because this happens at the same time with the heat decarbonization in the UK, and some old houses which still have 60 amp, for example. So it's quite limited in that context. They need to be upgraded to 80 amp. That becomes the default now standard for the UK to 100 amps. I think my house here got the 100 amps breaker, the fuse, so I can have a 22 kVA load.
Yes. Okay, thank you so much.
Thank you.
Okay, thank you. Due to the time is over, so I will thanks to Dr. Dhani, and we give applause for him. And thank you for the presentation and this nice discussion. I will bring back to Ms. Aulia. Silakan Bu Aulia.
Okay. Thank you very much for all the speakers and moderator for today. What an inspiring lectures. And we are almost at the end of today's session. But the next agenda, the head of the Department of Electrical Engineering ITS will give a closing remark. So let's welcome Dr. Dede Chandra-Riawan.
Thank you very much, MC. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, good morning, and good evening, everyone. And please allow me to have your precious time for this closing remark. And I promise it won't be long, maybe 3 to 5 minutes only. Okay, so today we have listened a very a good presentation, a remarkable presentation from our keynote speakers. Also, this morning we also have finished, or we have some parallel session for the papers accepted in this conference, and I hope all the idea and the progress of the research and the experiences could inspire all of and can inspire and can enrich our knowledge. Okay, for further research activities we are doing in this especially in the electrical engineering field. And also today we already listened a presentation from Professor Wolfgang Boss from Grace University of Technology from Austria. And from that presentation we have learned that we are ready to enter the terahertz era of a semiconductor. And I can imagine tera is very big number, 1 followed by 12 zeros. It's very significant number. And I think we need to check whether our conventional calculator still fit that number. Okay, and then from the second keynote speaker today, from Dr. Dani Pujianto, thank you very much, because from you we have learned that okay, we can reduce our carbon footprint, so it will be very helpful for slowing down this climate change. And one thing I agree with you, Dr. Dani, from now on please buy electric vehicles or electric car. And also special thanks to Professor Asari, Rector of ITS, and Dr. Iktot Edi Purnama, Dean of Electrics, for supporting this event, and also for giving opening speech this morning and this afternoon. And hopefully the speech can encourage all of our work in this pandemic situation. And also I saw some from the participant here. They are students from ITS and also students from other university in Indonesia, even from overseas. Thank you very much for your participation in this conference. And yes, I'm very glad because many students still have spirit to follow this session because usually during the afternoon many people already are fatigued and feeling tired, but still now up to this time, up to this hour, still we have more than 50-70 participants. Last but not the least, of course, our appreciation goes to organizer of ISITIA 2020. They already done a very good job, because it is a very challenging job during the pandemic for having this conference. And finally, I would like to wish you have a good evening, have a good rest, and stay safe. And I will see you tomorrow for the second day of the conference. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Dr. Dede Chandra-Riawan. So our last agenda is the virtual photo session, and we have around